In this video, we're going to talk about predicting some properties that are all relative to each other. By that I mean freezing and boiling points. Some substances are just easier to freeze than others, and let's find out why. So first off, I'm going to start out with the whole big summary right up the bat. So if you can get this from this video, you're doing good. So one, if we increase intermolecular forces, we're going to increase your freezing point. If we increase those same intermolecular forces, we're increasing boiling point. So if I ever ask you, how can you tell if a freezing point is high or low? You would say, well, how strong are the intermolecular forces? And then same thing for boiling point. So as we increase them, we're increasing the freezing point and the boiling point. But why is that? Well, the freezing point is the point at which the molecule finally slows down enough that those intermolecular forces can take over and start defining the shape of the liquid, and so hold it more rigidly, because that's what a liquid is. I mean, that's what a solid is, right, as compared to a liquid. So when it freezes, it's turning into a rigid defined shape, and so that point is determined and called the freezing point. Well, here's the thing. The larger the intermolecular forces are, the easier it is for that substance to kind of grab onto its neighbors and start forming a rigid lattice structure or some other type of solid structure. And so you can actually freeze at a much higher temperature. Whereas if you have really weak intermolecular forces, it's going to take you slowing those molecules down so much that they're hardly moving before they can finally grab onto their neighbors and form a solid. Boiling point is very similar. Here, instead of freezing, we're turning it into a gas. So we're turning a liquid into a gas, which of course requires energy. It requires heat. You're heating it up and you're starting those molecules moving like crazy. But at what temperature your substance turns from a liquid into a gas is determined once again by these intermolecular forces. If your forces are strong, that means your liquid forces, those intermolecular forces between the molecules in your liquid, are holding each other really tight. So it's going to take a whole bunch of energy to break through those forces, thus turning it into a gas that moves around really fast. And so that's why if you've got really strong intermolecular forces, your boiling point is also very high, because the energy required to break through those forces and allow those molecules to separate and move freely is much greater. All right, so let's look at this graph together. What trends do you notice? Look at the blue line first. This is group 4A. So carbon on the periodic table is right above silicon, which is right above germanium, which is right above your tin. And so with each of those, as you go from one to the other, they're all just binding with hydrogen. They all are bound to 4 hydrogens because, they've got 4 valence electrons, so they can bind 4 hydrogens. So they have very similar electronic and molecular geometries. What's the difference? The only real difference between these 4 different compounds is size, with SN being the greatest and carbon being the smallest. And so as you increase in size, remember what happened to those intermolecular forces? You're also increasing your intermolecular forces. And so in looking at that trend line, it makes a whole lot of sense that as you would go down a group on the periodic table, you're increasing the size of the molecule. You're still having the same types of intermolecular forces. They're just bigger. And so therefore, you're also increasing your boiling points. But what in the world is happening with groups 5, 6, and 7? They follow the trend starting at period 3, 4, and 5. That's a nice little trend, rising steadily through the ranks. But ammonia, hydrofluoric acid, and water, those are strange outliers. Why? Think about everything you've learned about intermolecular forces. Are there any other types besides the typical one that cause unusually strong bonds? I hope you thought and noticed that hydrogen, hydrofluoric, and ammonia all have hydrogen bonding components, because you got the nitrogen, the fluorine, and the oxygen. So even though they have that same dipole-dipole interactions that the rest of the group would have, theirs is a particularly strong version of the one compared to their neighbors. Okay, and so because of that, the trends are still valid. It's the stronger the intermolecular forces, the higher the boiling points, but it's just the reason they break through the trend when you're looking at the periodicity of the different boiling points is because they have a very strong intermolecular force compared to the rest of their group. All right, so kind of built into that last slide, I hope you notice that two things matter. So in addition to what type of intermolecular force and all that fun stuff. But there are two things that really matter when we're thinking about boiling points: electronegativity and size. So if you notice, carbon, nitrogen, oxygen, fluorine, electronegativity increases as you go toward fluorine. We have to take into account both the electronegativity, the size, the types of intermolecular forces, and then also the structure of the compound. And all of those things go into defining why these trends are. So if we look at period 2, we know carbon is less electronegative than nitrogen, which is less electronegative than oxygen. But fluorine is actually more electronegative than oxygen. So what happened there? It's because you have to look at bond strength and also the structure of water. And so there's lots of things that we can think about conceptually that make sense, but there's always outliers that kind of, you need more information to solve and think through, and that's okay. So basically this video is just to tell you the main components that you should use to guide your thinking. Does that mean you're always going to perfectly guess which molecule is going to have the highest boiling point? No, but it gets you talking points and gets you thinking through things that you need to know in order to think through trends. So as we said before, if we increase the IMFs, we're going to increase that boiling point. And those increased interactions could come from hydrogen bonding or the size of the atoms, or even how the molecules or the atoms, are separated in space with the geometry. But the same thing is still true. Whatever the different attributes are that go into building and strengthening the intermolecular forces, the more energy it's going to take to overcome these forces depending on how strong the IMFs are. An example of this is water. So water versus ethanol. Water has a 100 degrees Celsius boiling point, while ethanol is much lower at 78 degrees. So just looking at the boiling points, you know the intermolecular forces of ethanol are much lower than water. Why is that? Because if you look at oxygen, oxygen should be able to hydrogen bond in both situations. So there must be something else going on that makes ethanol so much lower, because they're both going to have both be polar molecules, so they're both going to have those dipole-dipole interactions. They're both going to have hydrogen bonding. So why is ethanol lower than water? Well, if you think about it as like a hindrance. So with water, there's plenty of room for extra hydrogens to hydrogen bond on both sides of the oxygen. But with ethanol, that CH group is all inside of the way of preventing kind of another hydrogen to come in freely. It's sort of like a crowded room. If it's too crowded, you may not be able to see the people you want to see. Okay, so you have to think more than just, hey, this is cut and dry. It's a big situation. And so there's a whole bunch of different things that must be taken into account and thinking through in order to predict boiling points and freezing points. But this is a good start. All right, so what was the rule about freezing points again? The stronger the intermolecular forces, the higher the freezing point, okay? Still true. The concepts that we talked about just a minute ago for boiling apply to freezing point as well. So with freezing point, this is me just kind of writing my thoughts down as to how I describe freezing point. So once again, the freezing point is just when the molecules slow down enough where the IMFs can take over and the liquids now can have a defined shape. And the freezing point normally rises when you're going down a group. Why? Because you're increasing the electron distribution, or you're increasing the number of electrons you have, and so you're increasing your intermolecular forces. Increasing intermolecular forces makes it easier for those intermolecular forces to hold the molecules or atoms in place once the motion of the group has slowed down enough, and therefore you have a larger freezing point. Okay. If the atom or molecule has a low IMF, then you need to slow the atom or molecule down even more, meaning colder, lower freezing point, in order to freeze the substance. Okay, so kind of in summary, increase IMFs, you're going to also increase the boiling point and increase the freezing point. The strength of your IMF depends on the types of intermolecular forces present, the size of the molecule, the structure of the molecule, a whole bunch of things. All right, so let's practice. Which has a higher boiling point? What do you think? Argon or xenon? Pause the video, write down what you think. I hope that you said xenon. Why? If you look at the periodic table, argon and xenon are both noble gases, but xenon is much larger than argon, which means it has an increased number of electrons, and so it has more options for polarizing and having that induced dipole. So its induced dipole intermolecular forces are going to be stronger, therefore it has a higher boiling point. What about calcium chloride or carbon tetrachloride? I hope this one is a little easier for you. So calcium chloride is ionic, carbon tetrachloride is covalent. Ionic bonds are much, much stronger than your covalent bonds. And so with this example, for instance, you've got calcium chloride is 1,935 degrees Celsius, whereas carbon tetrachloride is 77 degrees Celsius. And so in this case, ionic bonding makes a huge difference. You have a much higher boiling point because you have much stronger intermolecular forces. What about this one? This one's actually a little tricky, so write this one down. Which one do you think has a higher boiling point? Phosphorus pentachloride or water? I say it's tricky because here are the Lewis structures. If you look at the Lewis structures, phosphorus should be nonpolar. It's a very symmetric molecule, whereas water is very polar and it also has hydrogen bonding potential. So based on the intermolecular forces type alone, water should have a higher boiling point because it's got the strong hydrogen bonding, whereas the dipole, the nonpolar phosphorus pentachloride is instead relying on induced dipole interactions. But you'll notice it has a higher boiling point. Why? Size. Since it's so much larger than water, the size is actually going to win out over intermolecular forces. That's okay. The number one question I get on the exam is, what if it's an exception like this? Are you going to expect me to know all the exceptions? No, I'm not. I want you to justify your reason for why you do something. Something like argon and xenon, yes, I expect you to know which one is a higher boiling point. But something like phosphorus pentachloride compared to water, I want you to justify why you think it is the way it is. And so in your reasonings, you need to be discussing the intermolecular forces types, the size, the molecules, the geometry, all of this stuff that goes into predicting boiling point. All right, so then the last question is, which one has a higher freezing point? Well, it's the same. Higher boiling point, higher intermolecular forces, therefore higher freezing point. It's all about the same. So I hope this is a good intro. Don't worry, we're going to practice this a ton in class. So get ready for this. We're going to do all kinds of discussions and talking about how and why different molecules have higher or lower boiling points.